Okay, so now that we have all this information and knowledge about similar triangles, it's time to apply them. And we all know what that means, word problems. Yay, everybody's favorite. So let's start off with some basics just to remind ourselves of all the information that we know. First up, similar triangles are used to find unknown angles. Yeah, we know that. But also sides, not just the angles. There we go. So we get both pieces of information. Now, in order to do this, we're going to follow some steps. Okay, now this is going to be the same steps you're going to follow, and miraculously, these are relatively similar to all the other problems that we've been solving throughout the whole semester. But let's start off at the very beginning. Whenever we start with a word problem, we always want to use a let statement, or maybe two, depending on what the situation is. So introduce a let statement for any unknowns, and draw a diagram. This is something I've been trying to emphasize for a long time now, because once we can visualize it, it makes everything more clear. There's less questions because we can see what's going on. So once we have a diagram, what we want to do is we want to check to prove that those triangles have similarity, right? So check or prove triangle similarity. Let's write this. Check or prove triangles are similar. What does that mean? It means that they have proportional sides and equal angles. Don't forget that. And the symbol we use for similar is the tilde. All right. So we're going to use the properties of similar triangles, and that's going to help us set up equivalent ratios for the sides. Once we have those equivalent ratios, we're going to be able to solve for a whole bunch of data. And of course, there's other information that can apply to the problems too, depending on what's going on. So once we have all those ratios, we're going to solve for the missing information, and then we're going to be all done. So we're going to write a concluding statement. And that's pretty much it. Let statements, a diagram, proof that they're similar, get your equivalent ratios, find any missing information, write a concluding statement, and we're done. So let's try this out. So imagine that we have a tree that's 24 feet tall. Okay. It's going to cast a shadow that's 12 feet long. So let's draw that first. So we have a tree that is 24 feet tall. So imagine this is the tree. And it's going to cast a shadow which is 12 feet long. Now, if we think about this, that means this is 24 and this is 12. Now we can create a triangle out of this just by connecting these two lines here. And we can see that that's going to be a right triangle because trees stand straight up. Now there's this other person here called Brad. Brad is 6 feet tall. How long is Brad's shadow? Well, if we go 6 feet into here, now since it's the same time of day, we know that the angle of the shadow is going to be the same. So if we put Brad right here, and we know that Brad is 6 feet tall, our goal is to figure out, well, how long is Brad's shadow? Now just to be very clear on this 12 applies to this entire length here. Okay? Whereas the question is asking us how long Brad's shadow is. So that's just the piece inside. Well, that's our unknown. So our let statement is going to be let x be the length of Brad's shadow. So that means our x is going to go right here. Now it's just that piece. So the next step says once we've done our let statements, once we have our diagram, is we're going to check that the triangles are similar. Now we can see that that is also straight up and down because Brad stands in a nice straight line. Of course he does. So how do we prove that they're similar? Well, that means it's either two angles, or it's SAS, side angle side, or side 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 are proportional. So let's start off with what we know. Well, we know that both these angles are the same, but we don't know how to label them right now. So let's label our triangle. Let's call this angle A, this one angle B, and the end point angle C, which means we needed another name for the point right here where Brad is standing. Let's call that angle D. So looking at this, angle B and angle D have the exact same measurements. They're both 90 degrees. Okay, so angle B is equal to angle D. And they're both 90 degrees. That's basically given information. Anything else? Well, we can see that they both have angle C. They're both using angle C. So that's actually a shared value or a common value. So we can say angle C is equal to angle C this time. They're both the exact same angle. We don't have to come up with any clever naming or anything like that because they are actually the same angle. So we can say they are common. Oh, look, we have two angles. So we know that the triangles are now similar. So that we can say triangle ABC is similar to triangle. We didn't put a letter here, so let's put E right here at this angle, at that vertex. So ABC is similar to EDC. So now that I know those triangles are similar, I can start calculating for my ratios. Well, let's think about what our ratios are. So imagine I'm trying to find X, which is part of the small triangle. So that means that I want that to be on the numerator. So that means I want to calculate X, but what side is it over top of? The equivalent side for the large triangle. Well, that's the entire bottom of the triangle, which has a length of 12. All right, what else do we got? Well, we have the side of both triangles, and they're the equivalent side, the corresponding sides. So we could say the small triangle, which is 6 over 24. Now what do? We cross multiply. So we end up with 24x is equal to 12 times 6, which is 72. And then x is just going to be 3. So what do we calculate? We calculated the length of Brad's shadow. So that's our concluding statement. Therefore, Brad's shadow is 3 meters long. And that's the whole question. So we followed the exact steps that were laid out up here. We had our let statement. We drew a diagram. We checked and proved that the triangles are similar. We found some ratios, and we wrote a concluding statement. Now that's about as simple as the problem's going to come. So let's go do something a little bit more advanced now. So in this question, if you're looking in your course notes, the diagram is not super clear. So just take a look at what we're seeing here. We're seeing two sets of triangles, okay? And one of the sets of triangles, the back end of it, is crossing a river to the exact width of the river. So the question is asking us to determine the width of the river. So what we're trying to do is determine the length of side DE. That's our whole goal. Now, according to this, now I can draw and label on this diagram right here, but to be honest, it's kind of colored, and you're probably noticing the same issue where you can't really see anything. So I'm going to redraw it over here. So in this case, I have one long line that represents, one long line that represents one part of the triangle. That was pretty impressive. I'll try again. There we go. And we have another one that's going to go right across. There we go. So there's our two triangles. And it says that this one is 90 degrees and this one is 90 degrees. And this triangle is labeled as A, B, C. And this one is DEC. D, E, and C. It doesn't give us any other values in the picture, but it does give us lots of data in the question itself. Determine the width of the river. So our goal is to find the length of side DE. So we're going to let that be X. So let X be the width of the river. So let's label it on our diagram. It's going to be right there. Okay. But that's obviously not enough to actually solve this problem yet. So we need to fill out the information that we see. It says that AB, the side over here, is equal to 96 meters. Alrighty. Now these two are equivalent edges, so we may end up with a ratio with those two edges together. We also know that AC, so A down to C, is 204 meters. That's 204 meters. And BD, so B, all the way across this whole thing, the whole thing is going to be the equivalent of 396 meters. So if I drew a little diagram like this, that whole thing is 396 meters. So what can we do here? Well, we got to start off and make sure that we have similar triangles so we can start doing more work. So again, we need either two angles, side angle side, or three sides. Now, do we know all this information? Well, let's see what we know. We know that angle D and angle B are equivalent because those are both right angles. Okay, so we can do that. Angle D is equal to angle B. Awesome, because they're both 90 degrees. Don't have to really worry about that. What other angle do we know? Well, we have opposite angles here inside the points of the two triangles. So really, if we wanted to make these two triangles on top of one another, we'd actually have to flip it and then flip it again. So flip it vertically and flip it horizontally to actually make them work. But that doesn't matter. We can clearly see what's going on. It's just one triangle is upside down and flipped over to make to the next one. So, but we can see that angle C on both sides is equivalent because of the opposite angle theorem. So I can say angle BCA is equal to angle, so starting at the 90 degree, angle DCE. And this is due to the opposite angle theorem. Oh, and look at that. We have two angles that are equivalent. So we know that these are similar triangles now. So we can say triangle ABC is similar to triangle EDC. Triangle EDC. And that's because of the two angle theorem, similarity theorem. Okay, so now that we know that that's true, we can start to get information. Now our goal is to write a ratio. So we know that we want our x, and its equivalent side is the side AB, so that's 96. But now we need another one. What else do we know? We don't know two more similar sides, so we can't actually do that. So we need to find more information. So imagine that we wanted to do, let's say, DC over BC. DC over BC. Okay? The problem is I don't know the length of either of those values. Can I calculate them? Well, if we're looking at triangle ABC, I can actually calculate the side B. How can I do that? Pythagorean theorem. Because I already have two edges, I only need one more edge. That means I can do a squared plus b squared is equal to c squared. So let's do the Pythagorean theorem over here. All right. So that means that I have my hypotenuse. So where are we looking at here? Make sure that we're actually doing this right here. We are trying to calculate BC. Yes. Okay, so as I said, we need to apply the Pythagorean theorem. Sorry, I just need to pause for something. There was something wrong on my notes and I need to fix it up. But anyways, so we're looking at this top big triangle here, and we want to calculate for angle BC. Now, if we think about the Pythagorean theorem, it's a squared plus b squared is equal to c squared, where c squared is the hypotenuse. Okay, so that would mean that we have ab squared plus bc squared is equal to ac squared. Now let's fill in the information we know. We know AB is 96. And that's going to be squared. We don't know BC because that's what we're actually trying to calculate. So we'll just leave that alone. And AC squared is 204 squared. So let's rearrange this so we're solving for BC. So that means we're going to bring the 96 over to the other side. So we end up with BC squared, which is equal to 204 squared minus 96 squared. Okay? Now, when you do this math, you should remember we're doing the square of these, and then we have to take the square root of both sides to calculate for BC. When you do this, you should end up with the number 3. Actually, let's do BC squared first so we can see the whole number. When you do this, you should end up with a number here of 32,400. And when you take the square root of that, miraculously, you're going to end up with a number of 180. What is that 180? That is the distance of BC. Okay, so we now know that this, let me just switch my number up, my color up here, that this is 180. We just calculated that. So if I know that this is 180 and this whole thing is 396, that means I can actually calculate CD as well. or DC, I should say, DC. So I could say DC is equal to the whole thing, which is 396, minus the portion that we just calculated, which was 180. And what we end up with is DC is equal to 216. So again, we have another value. So since we have the two values we're looking at, which is BC and DC, we can actually substitute those values in now. So let's move things over a little bit. I'm just going to rewrite this over here. So that means we have x over 96, which is going to be equal to our DC, which is 216, over 180. And we cross multiply. So we end up with 180x is equal to 216 times 96. And then we're going to divide both sides by 180, and we end up with a value of 115.2 meters. X is equal to 115.2 meters. So what did we just calculate? We calculated the width of the river. So that's our therefore statement. Therefore, the river is 115.2 meters across. Awesome. So that's the end of this question. We still have a few more to go through, though. So this next question is similar to our first example, the one with the tree in the shadow. So it's going to be a similar shape, but it's a little bit more complicated this time in terms of its setup. But at the end of the day, it's really the same question. So let's try and figure out what we're doing here. So the foot of a ladder is 1.2 meters from a fence that is 1.8 meters high. Okay. The ladder touches the fence. So remember when it talks about the foot, it means the part of the ladder that's touching the ground. So the ladder touches the fence and rests against a building that is 1.8 meters behind the fence. Draw a diagram and determine the height on the building reached by the top of the ladder. So let's try and break that down. So it says that there is, just so I have lots of space over here, I'm going to do it over here on the side. So it says that we have a ladder that is 1.2 meters. The foot of the ladder is 1.2 meters from a fence that is 1.8 meters high. So let's draw the fence first. So we have a fence that is 1.8 meters. That was just stupendous. So let's try this again. So we have a fence that is 1.8 meters. Okay. So let's label that as 1.8 meters high. Great. But the foot of the ladder is 1.2 meters from the fence. So right about here, I guess. Okay. The ladder touches the fence and rests against a building that is 1.8 meters behind the fence. So that means that it's touching this and it's hitting a wall, or what's it touching? It rests against a building. Now here we're talking. Now this building rests 1.8 meters behind the fence. So that means this distance is 1.8 meters. So we know quite a bit of information. We know that the foot of the ladder is 1.2 meters from the fence. The building is 1.8 meters behind the fence. And we know the fence is 1.8 meters high. Now we know that buildings are straight and we know that fences are straight. Okay? That is amazing. Draw a diagram and determine the height on the building. So our goal is to find the height of the building here. This is what we actually want to find. Okay. So that's going to be our unknown. So let's let x be the height of the building. So we label it. There's our x. Now we got to prove that these triangles are similar like we always do. There's no difference. So we got to say is angle, angle, side, or side, side. I definitely don't have three sides to the triangles, so I can't do that. Side, angle, side. I don't have two sides with a contained angle. So that means I have to go for angle, angle in this case. So what angles do I have? Well, I can see that there are two right angles in here that correspond. So I can say, well, I better label this triangle first. I can't do anything until I fully label the triangle. So let's label it similar to the way we labeled the last triangle that looked like this. So we have A, B, C, this will be D, and this will be E. That means that angle B and angle D are equal. Okay. Because they're both 90 degrees. What else we got? Well, we can see that they both share this common angle C again. So we can see angle C is equal to angle C. So in this case, it's common. And there we go. We have two angles that are the same. So that means that we have similar triangles. So I can say triangle ABC is similar to triangle EDC. And this is due to the two angle similarity theorem. Great. Now that I know they're similar, I can just set up my ratios. So I'm trying to find x of the big triangle. So I'm going to make that my numerator. So x over the equivalent side on the smaller triangle, which is 1.8, the back wall of the triangle. Okay. And now I need to do another side. Well, what do I know? I know the bottoms of the triangles. So I can see the bottom of the small triangle is 1.2, but what's the bottom of the top triangle? It's not 1.8. 1.8 is just the distance. 1.8 is just the distance from B to D. We need to go all the way. So that means that it's the rest of this distance too. So, whoa, that kind of backfired on me. There we go. So it is 1.8 plus 1.2. So BC is equal to that whole thing, which is equal to, of course, just 3. So that means we can put 3 over top of our 1.2. So the entire bottom of the big triangle over top of the bottom of the small triangle. And what do we do here? We cross multiply like we always do. 1.2x is equal to 3 times 1.8. So what is that? 3, is that 5.4? 5.4. 5.4. And now I isolate for x, so I divide both sides by 1.2. And we end up with x is equal to 5.4 over 1.2. Or more simply put, x is simply just equal to 4.5 meters. And that's it. That's all the question was asking. We just need a therefore statement. It's just asking us how tall the building is. So therefore, the building is 4.5 meters tall. This is a pretty small building. 4.5 meters is not very big at all. Okay. So we have, pardon me, question number 3 done. Now we're going down to the final question. This one, you can see that the triangles are not on top of each other anymore. So there's no shared angles anymore. There's no common angles. That means we have to do all the work ourselves. That's okay. There we go. So a sailboat manufacturer wants to increase the size of their sails so that they can increase the speed by catching more wind. Makes sense. So that means that our triangle over here on the right is the original. Let's call this the original. And over here is the, scaled up large. Let's call it large. The large triangle, okay? If the area of the original, the smaller sail, is 600 meters squared. So we know that this area is equal to 600 meters squared. Okay. What is the area of the new larger sail? Do we have all the information we need? Well, we got to think about this one. We need to be able to set up a ratio. Now, we know, if we look at the question, it says they want to keep the same proportions of the side lengths while increasing the area. So since they're telling us that they are keeping the same proportions, we know that the triangles are similar. So since we know that the triangles are similar, we can simply just calculate what k is, the scaling factor. So let's do that. So let's say k of the small to big, okay, so k of the small is going to be equal to 45, which is our big guy, over the same corresponding edge on the small one, which is 30, and that's going to give us a value of 3 over 2. So that's our k factor. Now, if you remember back a lesson, we learned a property that said that if we have the area of one triangle, we can get the area of the second triangle simply by multiplying by the square of k. So that means the area of our large triangle is going to be equal to the area of our small triangle multiplied by our k squared. So area of a large, that's what I'm trying to figure out. So we leave that alone. Area of our small, we know from the question, is 600 meters squared. So that's just 600. And we're going to multiply that by k squared. What is k? K is 3 over 2. Squared. That's the same thing as saying area large is equal to 600 multiplied by 9 over 4. So when you do this, what you're going to end up with is with an area large of 1,350 meters squared. And that is the solution. There's nothing else to do on that question. What is the height of the new larger sail? So it wants us to figure out what the height of this new larger sail is. Can we do that? Well, what do we know? We know how to calculate certain things. We don't have any side lengths other than those bottoms, though, other than the base of the triangle. How can we do this? What other formulas do we know? We know the area of a triangle, so let's try that. So the area of the large triangle is equal to 1/2 times its base times its height. Well, man, do we have some good news, because we just finished calculating the area of the large. And the base of the triangle is given to us in the question itself. It's 45. That means the only variable here we don't know is h. Well, isn't that good news? Because that's what we're actually trying to calculate. So let's substitute what we know. 1,350 is equal to 1/2 times our base, which remember we're doing this of the new triangle, so that's a large triangle, so that's 45, times h. So now we just need to simplify and solve for h. So because we have a half here, I'm going to multiply both sides by 2. So that's going to give me 2,700 is equal to 45h. Now I just need to divide both sides by 45, and we end up with h is going to be equal to exactly 60 meters. That's a really tall sail. 60-meter tall sail. So that's it. That's the whole question. Therefore, the height of the the height of the sail is 60 meters. And that's it. So that's it for this second lesson. In the next lesson, we're going to be pushing the envelope a little bit, and we're going to get away from just looking at similar triangles, and we're going to finally learn trigonometry, which is the core of the entire unit. See you there.